Hello everyone, welcome back. I'm Alok Kumar, and yesterday I restarted the topic tangent and normal. Today, in this second and final lecture, I am going to conclude it. So let me now share my screen with you all. Okay, so let me give you some insight on what it means when you intersect a line with a curve. So, what I mean to say is this. Say, let's take an example, y equal to x squared. It's fairly simple curve, y equal to x squared, that is a parabola. And take the line y equal to x. So let me take the curve C, that is this x square, and then line L1, that is y equal to x. Now this line, if I intersect this line with this curve, then graphically I can understand that if I write like this, it will cut somewhere here. What does it mean when we say that find the points of intersection of this curve and this line? So this C and L1, if you want to solve simultaneously, then it means you want y equal to x square and y equal to x solution. If I equate them, I get x square equals x. So x times x minus 1 is 0. That is x is 0 or 1. When x is 0, y certainly is 0. And when x is 1, y is x squared, that is 1 square, that is 1. So I can say that the line L1 and the curve C, they intersect on 2 points 0, 0 and 0, 1. So for your benefit, I'm just writing these 2 points at 0, 0 and 0, 1. So this line L1 and this curve C, they intersect in 2 points 0, 0 and 0, 1. If I just change the line and curve is same, suppose I take the line L2 is y equal to 2x minus 1. Let's see why these are chosen, these coefficients 2 and negative 1. So if I again intersect this line with the curve y equal to x squared, that is a parabola and a line, it amounts to solving x squared is 2x minus 1. Now, the moment you solve this one, you will get x squared minus 2x plus 1 is 0. And you notice you end up with a perfect square. That is not purely coincidental, but let's investigate it. Let's forget. So you are getting x is 1 and 1. So algebraically, I am getting 1, 1. It means that tells you that this line L2 meets this curve at just one point. Means the points are repeated. We are getting when x is 1, that y happens to be 1. And again, x is 1, y is 1. So it means what we are getting is this one. If I make a diagram here, so I will make this is the curve, and you are getting this kind of thing. Say this is point 1 comma 1. This is point 1 comma 1. So let me just erase it or use a different thickness maybe. So let me use a different thickness. So this is 1 comma 1. And then this line is y equal to 2x minus 1. This curve, of course, C was y equal to x squared. This time, the line L1 and the curve C, they intersect at just one point. Let's call it P. So P1, 1. And as roots are double, we can say it intersects in P1, 1 and P1, 1. So sort of, there is just one point, but you understand that this is a particular thing. Here we say that this line is a tangent to this curve. It means the tangent intersect the curve in two coincident points. So it is coincident points, means points are just coinciding with each other. And algebraically, so that was geometrically, algebraically we will say that this implies that roots are repeated. So corresponding to P, corresponding to P, we get x is 1 and 1. This tells you this repetition of roots, that tells you that indeed at x equal to 1, the line y equal to 2x minus 1 is tangent to the curve y equal to x squared. So we expected this kind of thing and we got. So this is 1 1. And you see that this is tangent like thing. Say we discussion we take further by raising the degree of curve. So let's say the y equal to x cube curve, which itself is a fascinating curve. And those who have done calculus, they know that this is the source of many counterexample and many conceptual examples. So y equal to x cube curve. And now same thing, I will take line y. So this is curve C2, still line L1. And one I will take that curve C2 is y equal to x cube. And line L2 I will take as y equal to 3x minus 2. So I chose 2x minus 1, here 3x minus 2. Let's see how they interact. So if you come this side, then these two lines, rather one curve and one line, they intersect at the points given by x cube equal to x. So that means x cube minus x equals 0. I can take x out, x square minus 1 is 0. We can factorize and we get x equal to 0, negative 1 and positive 1. The corresponding y values are x cube, so that gives you 0, negative 1, 1. So it means the curve C2 and line L1 meets at 3 points. Let's call them P1, 0, 0, P2, negative 1, negative 1, and P3, 1, comma 1. If I sketch it, it's like going to be that we have got a curve and this line. So this line is simple y equal to x. This curve was y equal to x cube. And then together they intersect at this is P1. This was P1. And I labeled P2 as negative 1, negative 1. So this is my P2. And this is my P3. Anything you can name. So these 3 points. So this line intersect the curve in 3 points. Understandable. If this degree is 3, then if you eliminate y between them, then this polynomial of degree 3 you get in x. So it has at most 3 real roots. It has got at most 3 real roots. In this case, because coefficients are such that you get exactly 3 real roots and all roots are distinct. So you get 3 real and distinct roots in this case. And that tells you that the line L1 intersects the curve C2 in 3 distinct points, namely P1, P2, and P3. This scenario changes once we consider this 3x minus 2 line and curve same y2 equal to x, y equal to x cube. Now let me intersect this C2 and L2 where they meet. So I will get here that x cube equal to 3x minus 2. I can write x cube minus 3x plus 2 equal to 0. And if you notice, suppose I call it f of x, it does not take long to notice that f of 1 is 1 minus 3 plus 2 is 0. And so I can factorize this. So x minus 1 is a factor. And the other things I can write, as I told you yesterday, that first fix the highest term, that is x squared, because this can only be obtained by coefficient 1 and 1. So this is 1. Then fix the constant term. This is negative 1, you want plus 2, so negative 2. Because the highest and lowest term can be obtained only by multiplying these two highest and these two lowest. In between, we have got, say, this is a of x. So I can equate coefficient of x square on both sides. On left hand side, this coefficient on this side is 0. And in this expression, this coefficient is first x square will give you a. And then this will give you from here negative 1. And so a equal to 1. So we get a equal to 1. So we can factorize it further by writing x minus 1 times x square plus x minus 2 equal to 0. And still we see that 1 is again a root, so x minus 1 and times x plus 2 equal to 0. So you get here like x minus 1 whole square. We just love it. X plus 2 equal to 0. So you get the roots at 1 and negative 2. Compare the left side. You got here 0, minus 1, all three distinct. 0, minus 1, 1, all three distinct. Here 1, 1, minus 2. It means you get one root repeated twice and one only once. So it means you get two distinct roots. So still polynomial is third degree, x cube, but then right now the natures of root are different and you are getting 1, 1, negative 2. Now if you plot it, this only will tell you that if I were to draw this diagram, that here it is the curve y equal to x cube and x equal to 1. So if I have to do like this scenario is like this, that this point P1, so P1 and say P2, P1, P2 becomes the same point. This is P1, this is P2, they become the same point, and so they coincide. So this is 1 and x is 1, y also is 1, and here you have got this x is negative 2, and then y is your x cube, so this is negative of minus 8. You can also get it is y equal to 3x minus 2 because they lie on the line also and curve also. So P1, P2 and P3. So in effect, we got here just two distinct points. At one point, the curve is touching it, other point is intersecting. So here touch means a special kind of intersection, and this is simple intersection. This is simple intersection. This is a special intersection which we call touch. The curve touches it. So it means we got this kind of our conclusion, that suppose you have got a curve like y equal to some degree f of x, or it may be g of xy. So like maybe y equal to x square minus x cube, or y square minus 2xy plus x cube, anything can be there, or simply y equal to fx. So if some curve is there, and if you intersect this curve, so these polynomial curves, y equal to ax plus b, then if these two intersect and you find the roots of polynomial in px, some polynomial px, you find the root. If roots are repeated, that means that at that point, the curve C and the line L touch. If they are not repeated implies they intersect. Repeated twice means alpha, this type of root. So this we will keep in mind when we do problems of this sort, that we are looking for this quadratic factor. This signals the fact that corresponding to 1, the point on the curve is such that the line touches the curve at that point. Here we have got the point 1, 1 at which the line 3x minus 2 touches this curve. And in the first example, it was that y equal to x was intersecting, but y equal to 2x minus 1, that line was tangent. So we drew it here that 2x minus 1 was indeed a tangent at the point 1, 1. So it means this line meets at just one point, not at 2 points. Both are coincident. Okay. With this background, and one more thing, we will proceed. One more is this. Suppose y equal to ax square plus bx plus c is some quadratic curve, second degree curve, say second degree curve. So assume a is not 0. And suppose you want to find that the line y equal to mx plus n, I'm avoiding c because c is used here. So I want to find this curve and this line. If I want to say that if I know that this line L touches curve C, then What is the relation between these coefficients? That we just answered. Algebraically, we will say that the intersection of some curve, say curve is like this here, and some line, that amounts to solving the equation ax squared plus bx plus c with mx plus n. So it's a quadratic. So it is ax squared plus b minus mx plus c minus n equal to 0. And we know that the roots are repeated. And if roots are repeated, it means that for quadratic case, discriminant is 0. And that gives you b minus m whole square is 4 times a times c minus n. So this imposes a condition on the constants a, b, c, m, and n such that this line is a tangent to this curve. So this is my condition for touching. Line L touches C. It is for second degree. So discriminant is good. If it was not second degree, say suppose y equal to mx plus n is there, and the other curve is y equal to some x to the power d. So x to the power some kind of, or let's to the power k, where k is degree, and this is axk, and other thing can be there that I don't care. So in this case, you are solving a x to the power k, and plus this is mx plus n. And then you are saying that when they will have equal roots, if they touches, so it means f of x is this expression, axk, this polynomial, and this kind of thing. So here we need that at that point fx naught is 0 and f prime x naught 0. If there is such a point x naught such that both are 0, this will mean that x naught is a root repeated twice of the polynomial fx equal to 0, and so we can again say that x naught touches. So this is it. And now let me apply these concepts to a problem. So here we go. So it is given that tangent at the point P 1 comma 1 and to the curve y square equal to x 2 minus x square, say take y greater than equal to 0, this curve. So tangent at P1 to the curve meets the curve again at Q. Our job is to find Q. Means I repeat the problem. The tangent at P11 to the curve y square equal to x times 2 minus x whole square. Y is non-negative. That meets the curve again at Q. You have to find Q. The solution would run like this. It is given that this is tangent at P11. First of all, we write y square is x times 2 minus x whole square. Differentiate with respect to x. So 2y dy over dx is x times 2 times 2 minus x negative 1 plus 2 minus x whole square. That gives you, because point is 1 comma 1, so let me put the values 1 comma 1. So 2 times dy by dx at say point 1 comma 1 is 1 times 2 times 1 times negative 1 and plus 2 minus 1 whole square. That gives you minus 2 plus 1. And so we get dy over dx at the point P is minus 1 over 2. So it means we get the equation of the slope of tangent. The slope of tangent at P to this curve, this may be any curve. We don't care much about this curve. So this we get at minus 1 over 2. Now, we can write equation of tangent at P. That is, this is slope. So my equation will look like x plus 2y equal to some constant, say k. And because 1, 1 lies on it, so I can put here 1 plus 2 into 1. So x plus 2y equal to 3. That is x plus 2y minus 3 equal to 0. This is a shortcut. Those who are used to y minus y1 is m times x minus x1. They can use that, but please master this one. Here I just set up the left side by thinking that minus 1 over 2 is the slope of the line. So that was fixed by slope, and constant has to be there. Constant will be fixed by one point that passes through the line, here given to be 1 comma 1. So x plus 2y is 3 is the tangent to the line, and says roughly our situation becomes that some curve is there, and then we want to find out that how x plus 2y minus 3 intersected. This is a tangent to this at point P. This is tangent, mind you. And then your curve is y squared is something. This may not be this curve. It is just one sketch. So what I will do, I have to solve the curve as in the theory example. C is y square is x times 2 minus x whole square. This curve is to be solved with this line, which we have found that x plus 2y minus 3 equal to 0. So you have to solve them simultaneously to find the value of x. So you have to eliminate one variable. Here y is easy to eliminate. So I will write here y is, from here I will get y as 3 minus x over 2. And I can put this y here back in this equation star. And so I will get here that 3 minus x by 2 whole square, and that equals x times 2 minus x whole square. I can expand that. I'll get 9 minus 6x plus x squared. This 4 comes here. 4x 2 minus x whole square. So that is 4x, and 4 minus 4x plus x square. Let us expand this side. So I will get 16x minus 16x squared plus 4x cube. And this, when I transpose everything to this side, so 0 equal to 4x cube minus 16x squared, and this one, so minus 17x squared, and plus 16 plus 6 will become 22x, and this is negative 9. So I will end up with 4x cube minus 17x squared plus 22x minus 9 equal to 0. Let's assume for the moment, let's pretend for the moment that we don't know its special roots. So it's like a polynomial, call it g of x, some polynomial. So obviously we will like to find first integer roots. And when we check, we find that g of 1, if you write g of 1, so let's check g of 1, that is 4 minus 17 plus 22 minus 9, that happens to be 0. So with this knowledge, I can factor it, and I can write this as x minus 1, and I told previously, here write 4x squared, because this 4 can come only from here and this term, so 4x cube. This you leave right now, call it px, and plus this constant term can still come from here. This is negative 9, this is negative 1. So this in fact will be plus 9, so that product is negative 9. To get coefficient of x, equate anything, say x square coefficient on both sides. So x square coefficient here is minus 17. From this side, x into x square, so that is negative of p, and this is negative of 4. So negative of p, and this is positive of p in fact, and this minus 4. So we'll get p equal to minus 13. So we'll again get here x minus 1 times 4x square minus 13x plus 9 equal to 0. Just check. Again, 1 is a root because 4 minus 13 plus 9 is 0. And so I can write x minus 1 times x minus 1 is a root. And this is 4x because 4x squared. And this must be minus 9. So we got this kind of result. So in fact, we got x minus 1, 2 times, and 9 over 4. You can shorten the work. That's what the message was. We can shorten the work. So think here, come back here. After we get this, after this stage, let me change the color. After this stage, what we do is that we know that this is the intersection of this line and this curve, line and curve. And we know that line is tangent at some point, and that point correspond to x equal to 1. Y, of course, was corresponding value. So x equal to 1, it corresponds to this point. So it means that in this one, I expect 3 values of x, perfectly 3 values, because this is degree is 3. Of them, 2 I already know. 2 I know. Because x equal to 1 root has to be repeated, I have to get 1, 1. And third root, let's denote by x3. This I do not know. So I apply now product of roots. So product of roots I apply. So that is 1 times x3, product of roots. And that is equal to negative of this one. So negative of negative 9 over 4. Don't make calculation mistake. So this is 9 over 4. So I get x3 is 9 over 4. Perfectly fine, as we get here x3 is 9 over 4. So it means we know that, let's scroll up. We know that this line which touches this curve at the point P, which was 1 comma 1, and this curve was y squared is x, 2 minus x squared, which thankfully we did not have to plot. That could have taken time. So we just thought that, okay, there is a line which is tangent to this curve at some point P. Say that point was this one, 1 comma 1, and this of course meets again at Q, and this Q I wanted to find. So I found by this one here that in fact, because this kind of thing was there, so we found P, this root was 1, 1, and so this Q corresponds to x equal to 9 over 4. The moment I write x equal to 9 over 4, and then y I can get, y is x, 2 minus x whole square. So that is 9 over 4, and 2 minus 9 over 4 whole square. That gives you 9 over 4, and times, we can still get, this is 8 by 9. So you will get here, this is 1 by 4. So this is 1 by 16. And so 9 over 64. And so this kind of thing we will get that, but that was y squared. So your y is 3 over 8, and because y is non-negative, and so you will find that the point happens to be 9 over 4 and 3 over point. This is the point Q at which this tangent at P meets the curve again. So here I used the concept of repeated roots. Here I used the concept of repeated roots. If L happens to be a tangent to C, then corresponding x is repeated, and so we are able to finish this problem. Let's take another problem. Let's take another one with some different kind of concept. So here it is telling you that, say you have got, it remains same. So now you are saying that consider the curve 5x to the power 5 minus 10x cubed plus x plus 2y plus 6 equal to 0. This is the curve, and you are given that the normal at p 0 comma minus 3 to this curve to C that meets the curve to C meets it again at 2 points. So your job is to find these points. Now they are saying 2 points. We are not saying what kind of points, so we'll debate on this 2, whether it is 2 or more. So now let me first write normal. Now first of all, we'll write, this is equation of curve as this is 5x5. So solution will proceed like 5x to the power 5 minus 10x cubed plus x plus 2y plus x equal to 0. Differentiate it with respect to x. So you get 25x to the power 4 minus 30x squared plus 1 plus 2 times dy over dx. is 0. And if you evaluate this at the point 0 minus 3, you will get here this all will become 0, 0, 1, and plus 2. This is dy by dx at the point 0 minus 3. So you will get dy by dx at that point p, which is 0 minus 3. That gives you negative 1 over 2. So this is the slope of tangent. We need not sketch this curve. So this is the slope of tangent to the curve at point P minus 1 over 2. And the so slope of normal is going to be negative of 1 upon negative 1 over 2. Or simply you can turn it over and change the sign. So that is 2. So slope of normal is 2. And same equation of normal can be 2x minus y is something constant and passes through 0 minus 3. So 2 times 0 minus 3, and that is plus 3 rather. So you are getting 2x minus y equal to 3. So you're getting 2x minus y equal to 3 is the equation of normal. Equation of normal, it's still a line, call it L. So now my question is that some curve is there, some curve, and then some line is there which is normal at some point. At some point, some normal is there, some point. Say this P point is 0 minus 3. I'll call it L. This is my C. It does not matter what my sketch looks like because I am doing analytical derivation, not on the strength of how the graph is plotted. And that's entirely not needed. Now, so I am interested in how L and C interact, means intersect. So how L and C interact. So I'll say this interact as how they will intersect, where they meet, how they meet. They may not meet, they meet more than once, or what kind of meeting is it? So that means that solve this L with the curve C, which was given as 5 to the power 5 minus 10x cube plus x plus 2y plus 6 equal to 0. So you have to solve simultaneously this curve and this line. We see easily that we can eliminate y between them. So let's do that. 5 to the power 5 minus 10x cube plus x plus twice y. Y you can put. So this gives you y is 2x minus 3. So we write 2x minus 3 and plus 6 equal to 0. That leads to 5 to the power 5 minus 10x cube. And this becomes plus 5x, and minus 6 plus 6 becomes 0. And so you get a wonderful thing. This is 5th degree quintic. This is called quintic. So 5th degree. 4th degree is called quartic, or you call it sometimes biquadratic. And you know second and third is cubic, second is quadratic. So this quintic polynomial you get 5th degree. In general, you can't solve 5th degree, but here it is special. Once you take 5x is anyway 5x is out, and then you are getting x4 minus 2x squared plus 1 is 0. That's lovely. It's just perfect squared. So x squared minus 1 whole square is 0. I can write x into, I can factorize, and x minus 1 whole square, x plus 1 whole square is 0. So this line L and this curve meets at some point such that x coordinates are given by x equal to 0 and then 1, 1, negative 1, negative 1. Now watch out. This is repeated twice. This is repeated twice. In fact, this also repeated twice. This both repeated twice. What's the conclusion? That means that the line L touches the curve C at the point corresponding to x equal to 1 and x equal to negative 1. It means that it must have been something like this, that this kind of thing, that here it is 1 corresponding to point x equal to 1, x equal to negative 1, and then here it is just normal. So it means this kind of thing is there, that at 2 points is tangent, at 1 point normal. Basically you get 5 points, but these 5 all are not distinct. Only 3 distinct real roots, and two roots repeated twice. So repeated twice means touching. Geometrically it is touching. So it means, let me find the point now. So when x equal to 1, because the point lies on both curve also and line also, so I will take the line is the simple one. And so your line is 2x minus y minus 3 equal to 0. That is y is 2x minus 3. So at the point 1, this point is given by x is 1 and y is 2 minus 3 to negative 1, and this point is negative 1, and minus 2 minus 3 is negative 5. So we know that this L meets, in conclusion, L meets C at 3 points. 1 point already given, that was normal, so that was 0 comma minus 3, that was P at 1 point. Here it is normal. It also meets them at points Q and again at R, where at Q, where this is 1 minus 1 and R is negative 1 negative 5. Here it is tangent. So it means this line L, the line L, that was a big line, 2x minus y minus 3 equal to 0, and some curve which was further 5x to the power 5 minus 10x cube plus x plus 2y is carry, 2x plus y equal to 0. But analysis is very simple. Analysis was quite simple. And we showed that in fact this line L meets the curve C in following manner, that it is normal to the curve at the point p0 minus 3 and tangent at 2 points, 1 minus 1 and minus 1 minus 5. And that's what we conclude, that okay, so this is what we are getting. So let me change the color and say something different. So one example I will take, which will tell you the common tangents, that also always a favorite of JE paper setters, common tangents. So let's understand with the help of an example that you have got a point, that suppose we have got two curves. Let's call curve C1 is y equal to x square plus 4x plus 8, and curve C2 let's call y is x square plus 8x plus 4. This 8 and 4 are swapped, but that does not matter. Simply there are two quadratic curves. So these two curves are given. I want to find the common tangent to them, and also points of contact P on C1 and Q on C2 of the common tangent. So I want both these things. So how to start? So I'll say that okay, there is a line which is common tangent. I need not draw any diagram. So I will say that okay, let the line y equal to mx plus c, this line be a tangent to the curve. Let the line y equal to c, y equal to x square, curve c1 x square plus 4x plus 8. Okay, if this is a tangent to the curve, it means if I solve the line with the curve, that is x square plus 4x plus 8 is mx plus c. If you solve it for x, so let's rearrange the quadratic. X square plus 4 minus mx, 4 minus m times x plus, let me erase and let me write it again so that, okay, so if you write x square plus 4 minus mx plus 8 minus c equal to 0. So if I solve it for x, means if I solve this quadratic, I expect to get repeated roots. But it's a quadratic, so it means I expect to get equal roots alpha and alpha. The condition is discriminant equal to 0, and that implies that b squared equal to 4ac, and that we can simplify a bit. And we can write here that 16 minus 8m plus m squared is 32 minus 4c. That gives you m squared and minus 8m plus 4c minus 16 is 0. So we get this kind of thing, that this is the condition, condition on constants or parameter on constants, such that this line L, y equal to plus c, is a tangent to the curve y equal to 4s plus 8. Let's do the same thing for, because it is also a tangent being common, also is tangent also a tangent to the curve C2, that is same type of curve, just coefficients are changed, 8x plus 4. It means that mx plus c equal to x square plus 8x plus 4. This also should have, this has equal roots. So let's arrange them. X square plus 8 minus mx plus 4 minus c equal to 0. And if I do that, then I will get again discriminant is 0, which gives b squared is 4 times 4 minus c, 4 minus c. And so you will get 64, expanding 64 minus 16m plus m squared is 16 minus 4c. So m squared minus 16m and then plus 4c and then plus 48 equal to 0. So you got this as the condition for being tangent on MC, and one more was the boxed one. So these two. So let's call it a star. Let's call it star star. Means two equations, two unknowns m and c. I can find the value. So I see most of them cancel. So I just subtract first. When you subtract, c goes away. So when you subtract, you are getting by subtraction of star star from star or other thing, you are getting here minus 8m plus 16m, and minus 16 minus 48 is 0. So you are getting 8m minus 64 is 0, and so you are left with m equal to 8. So m equal to 8 is one answer. Now c I can get from anywhere, and so I just plug in here. So C is getting from, say, the other one is this one, that m square minus 8m. So I can write 8 square minus 8 into 8 plus 4c minus 16 is 0. And so 4c is 16. We get c equals 4. So we get c equals 4. So we get m8 and c4. So we know now that y equal to mx plus c, that is 8x plus 4. This is the line, that is common tangent to curves C1 and C2. This is about the common tangent. Now suppose I also want to find points P and Q, say something like that, why this is the, if this is there, then how this, that where they meet. So say some this kind of curve is there, some this kind of curve is there, suppose. So you want to also find out that where it is meeting. So let me check, let me draw it properly. And so this is this, we are good. So something like this kind of thing, that if you have this kind of thing, so you want to find out how they are touching. This is P and Q, some P and Q, some rough. So now if you want to find this one, so remember the curve C1 was x square, curve C1 was y square, curve C1 was y equal to x square plus 4x plus 8, and curve C2 was y equal to x square plus 8x plus 4. And we now know that the line 8x plus 4 is tangent. So we can solve again to find x, but something better I will do. If some line is tangent, come here, we have used that this discriminant of this equation, discriminant of this one, this discriminant, I have used that discriminant of this is 0. If discriminant is 0, means the value of x, call it x naught, is nothing but minus b over 2a. In any quadratic, ax square plus bx plus c equal to 0. X equal to minus b over 2a is the vertex. And if you make this is 0, this is not 0, then it means it's a perfect square, and that happens at the vertex only, minus b over 2a. So I can shorten my work. I After finding, I can write that, okay, x naught is negative of b over 2a, negative of 4 minus m upon 2. So negative of 4 minus m, and m I got as 8. So 4 minus 8 by 2. So negative of minus 4 by 2. So that is 2. So it means we can say that indeed this line L meets this curve at the point x equal to 2, and y I can calculate from the line itself, or I can calculate from here. So y is x square plus 4x plus 8, so that is 2a square plus 4 into 2 plus 8, that is 20. So I will say that this line L meets the curve x square plus 4x plus 8 at the point 2 comma 20. That line was y equal to, we got the line also, y equal to mx plus c, and as you saw that m was 8, so line was 8x plus 4. And for q, again scroll back, and we see that it was this kind of thing, x squared. So x naught is minus 8 minus m by 2 into 1. So minus 8 minus m is 8 only, so that is 0. So it means here x naught is 0, and y is x square plus 8x plus 4. That gives you y equal to 4. So it means you find that at this point q, this is 0 comma 4. So it means this line L meets one of the curves C1 at this one, C1 at 2 comma 20, and C2 it meets at 0 comma 4. Remember, if you equate them, had you equated, you will get the same thing. Suppose you equate these two, x square plus 8x plus 4 is 8x plus 4. So x square equal to 0. That tells you 0, 0 repeated. If you get x square plus 4x plus 4 is 8x plus 4, this kind of thing, you will get now. So this is 8x plus 4 and 4x plus 8 it was. So let me just write again. So x square plus 4x plus 8 was 8x plus 4. You will get x square and minus 4x plus 4 is 0. Again, x minus 2 whole square is 0. This whole squared. It means again 2 and 2. So we have found the common tangent, and we have also found that common tangent meets at some special point. That point is given. Okay, let's move forward. So now the problem I want to do is that you want to find application best thing, normal. So you want to find shortest distance between say two curves. Mind you, curve is a generalized word, it can be one line also. So first example I'll take is y equal to x square plus 3x plus 2. This is a curve parabola C, and line is y equal to x minus 2. I want to find the shortest distance, which is called SD, shortest distance between line L and C. Or put this way, that let P be on L and Q be on C. Then find PQ least, PQ least or PQ minimum. So it means as P moves on this one, so this curve can be drawn like this, that so this is this kind of thing, this parabola, and y is x minus 2. You will find that this is this curve. So this is y equal to x square plus 3x plus 2. So you say that x equal to 0 to this, and this kind of roots. And here, if you go, this is y equal to x minus 2, which I will write as x minus y minus 2 equal to 0 is the line. This is the curve. So there is a line and curve. I want to find shortest distance. You see, if you go far off, this distance, this distance, this distance. Among all these distances, I want the one which is the least among all distances. I want the least distance. So it is like this, that if it is least distance, it means that what we will do, that our method would be, this is one parabola something, this is one line. I will try to find out that the point on the parabola, say P, such that the tangent at P, the tangent at P is parallel to the line L. So the tangent at P, this is the tangent at P. So tangent, this is tangent to curve C at P. I will make it parallel to line L. If this is so, then this point, from this point, if I draw perpendicular, this will be my shortest distance. That is my ST, shortest distance. So it means our job is to find a point on the line such that the tangent at that point is parallel to this given line. That's easy. Let me take on this parabola y any point as t and t square plus 3t plus 2. Means I have just made x equal to t and y equal to t square plus 3t plus 2, a simple parameter, not much of a thought. Now dy by dx at any point is dy over dt over dx over dt. That gives you dy over dt. So this is 2t plus 3 over dx over dt, that is 1. So it is 2t plus 3. So let's review what we did. What we said was that we wanted to find the shortest distance between this line and this curve. So we wrote like this one. And then I'm saying that if I'm able to find a point P, if I'm able to find a point P, now that's clear. If I'm able to find a point P on the curve such that tangent at P is parallel to L. So tangent to the curve C, this is C curve, at P is parallel to line L. Then this point here P we have found, and if I draw perpendicular, suppose this is Q, then these are the points P and Q, and shortest distance is also PQ. That's my approach. So I'll write 2t plus 3. That 2t plus 3 is there. Now we know the slope of line. The line is x minus y minus 2 is 0. So slope of line is 1. So I want 2t plus 3 is 1. That is 2t is negative 2. So t equal to negative 1. If I get t equal to negative 1, then my job is done now. The point P happens to be, because t is minus 1, so x equal to t and y is t square plus 3t plus 2. So negative 1. This is 1 minus 3 plus 2, that is 0. So point P happens to be minus 1 comma 0. That's fair enough. So point P we got. So we updated the diagram and something we got. This vertex was this curve was x square plus 3x plus 2. So if I draw it, let me draw it in the, let me erase it and draw it here as the graph paper. So y equal to x square plus 3x plus 2. If you accurately draw, this has got roots at x plus 1, x plus 2. So you are finding that minus 2 minus 1 and x equal to 0. This value y is 2. So and vertex is minus 3 over 2, here minus 3 over 2. So you find that this goes like this kind of thing. Here this is minus 2, this is minus 1, this is negative 3 by 2, and this is something. And the line is also going. Now we have found point minus 1 comma 0, minus 1 comma 0. It means minus 1 comma 0 is this one. X is minus 1 and y is 0. So obviously you are checking that x is minus 1, and then so it will come minus 1 plus 3, so it is 0. So minus 1 0. And other we have, so this is this kind of thing. And here we have got a tangent. That equation of tangent is y x minus y, x y equal to x minus 2 line. So I wrote x minus y minus 2. Okay, so I wrote x minus y minus 2, which this was a line. Now you will find that tangent at this point P, tangent at point P, this tangent is the one which is parallel to this line. This tangent, so is equation is that we already got this one, t is minus 1. So it means you have got this point as minus 1 comma 0, and because tangent at this point is parallel, now let me find the slope of tangent. So that slope of tangent is 1. So it means if this is 1 and passes through minus 1 comma 0, so this line, this tangent line, call it t, this t is nothing but slope is 1, so this is x minus y, and passes through minus 1 comma 0, so this is minus 1, so x minus 1 plus 1 equal to 0. So we have found out that this tangent is x minus y plus 1 equal to 0. Of course, they are parallel lines, distance is anywhere constant, but only one point lie on the curve, so this distance I will take. And so distance is, you can find either distance of minus 1 0 from, so distance of minus 1 0 from, you can say this point, that is x minus y minus 2 equal to 0, which is minus 1 minus 0 minus 2 upon root 2 mod, that is 3 over root 2. Or you can also find distance as distance between parallel lines. So lines are x minus y minus 2 is 0 and x minus y plus 1 is 0. This is a line which passes through some point on the curve and parallel to the given line. So distance between lines, that is given by 1 plus 2 upon root 2, that is again 3 over root 2. So this is the distance, and the point P and Q on this line. So point P is minus 1 0, and what is Q? So this is minus 1 0. I also want Q such that the distance is minimum. So this Q is nothing but foot of perpendicular from P on this line. Let me write x minus y minus 2 equal to 0. This is the line. And then when you want to find, let me write a bit. So this is minus 1 0. You want to find foot of perpendicular. For that, suppose alpha beta is the foot of perpendicular. For that, the result is alpha plus 1 beta minus 0, and this is negative 1, this is negative 1, minus 2 times, and then you can put here minus 1 0 here, so that is minus 1 and minus 0 minus 2, and upon 1 square plus 1 square, so minus 2 times, this is minus 3, and upon 2, so that is just 3. So alpha happens to be 3 minus 1, that is 2, and beta happens to be minus 3 plus 0, so beta happens to be minus 3. So this point happens to be 2 minus 3. Let me check this point. Alpha is 2, all right, and beta is minus 3. So this calculation, let's check. Alpha plus 1 upon 1 is beta minus 1 upon negative 1, beta minus 0 negative 1. That point was minus 1 comma 0 that we found out, minus 1 comma 0, if you remember. And this is foot of perpendicular, so I need not have this negative of 2 because that is found for deflection. So this won't work. And so calculation I can again change. I can write this is negative 3. So negative 3 upon 2. So this is 3 over 2. So now alpha is 3 over 2 minus 1. So alpha is 1 over 2. And your beta is negative of 3 over 2. So if you take this as the point, so if you take now the point as this point as half and minus 3 by 2, we are good because we can check our answer that this first lies on it, because half plus 3 by 2 minus 2 is 0. And then this slope I can get by 0 plus 3 by 2, and upon minus 1 minus 3 by 2, minus 1 minus 1 by 2. So that is 3 over 2 upon minus 3 over 2. That slope is minus 1, and this slope was 1. So indeed this is the point. So it means we will say that points P minus 1 0 and Q half and negative 3 by 2, these are the points P on the curve P on the line, P on the curve C, and L and Q on the line L, such that PQ is the least distance between C and L. So this is the kind of thing that we do. So this example was the tricky one, and then you are expected to get this kind of thing. I have done line and curve. You can also get a problem on both curves, but principle remains same. And so in general, the shortest distance occurs along the common normal. And so for curves, we can do this thing exactly. So that's all for today. Let me stop sharing and okay, so that's all for today. Let us connect again tomorrow.